two-pole breaker is required when each heater has a neutral and two hot wires operating at 240 volts. A single pole breaker would only interrupt one of the hot wires, leaving the other hot and creating a significant safety hazard. Now, why is a one-pole tie breaker not preferred? A one-pole tie breaker doesn't offer the same safety level as a two-pole breaker. If one pole of a tie breaker trips, the other pole might remain closed, leaving one side of the circuit energized. This situation could lead to an arc fault and pose a fire hazard. It is possible for one pole of a two-pole breaker to trip while a heater is on. This could occur if, firstly, there is a ground fault on one side of the circuit, secondly, the heater is faulty and draws too much current on one side, or thirdly, there is a loose or damaged wire connection on one side. In such instances, the affected heater would shut off, while the other heater could continue to operate. Always ensure the circuit includes a ground wire. Verify that the wire gauge is appropriate for the amperage draw of the heaters. The heaters should be installed and maintained properly to avoid safety problems. In conclusion, while a two-pole breaker can power two 240 volt heaters on the same circuit, it's essential to understand the potential risks and ensure the circuit is installed and maintained to code. A one-pole tie breaker is generally not recommended because it does not offer the same level of safety. It's important to elaborate on the necessity of a two-pole breaker in this setup. With 240 volts heaters, we're dealing with two live wires, each carrying 120 volts relative to the neutral, combining to give you 240 volts between them. Think of it as two separate 120 volts circuits working together. The two-pole breaker is designed to disconnect both of these hot wires simultaneously if a fault is detected. This ensures that the entire circuit is de-energized, preventing electrical shock or fire hazards. Now, let's consider what happens if you were to use a single pole breaker. A single pole breaker, as the name suggests, only interrupts one of the hot wires. If a fault occurs and the breaker trips, only one of the 120 volts legs is disconnected. The other 120 volts leg remains live. This creates a dangerous situation, as someone working on the circuit might assume it's dead because the breaker is tripped, but they would still be exposed to potentially lethal voltage. Furthermore, even if the heater isn't being actively used, the live wire can still energize parts of the appliance, creating a shock hazard. A tied single-pole breaker, also known as a two-pole common trip breaker, might seem like a safer alternative. These breakers have a physical connection between the two poles, so if one pole trips, the other is supposed to trip as well. However, they are not designed to handle the specific requirements of a 240 volt circuit in the same way a true two-pole breaker is. The main issue is that tied single-pole breakers are primarily intended for multi-wire branch circuits that share a neutral. In such circuits, each pole carries 120 volts to different loads, and the shared neutral carries the imbalance between the two loads. If one circuit experiences a ground fault, the tied breaker trips both circuits to prevent overloading the neutral wire. However, in a 240 volt circuit, there is no neutral current under normal operating conditions. The current flows from one hot wire through the load and back to the other hot wire. The tied single-pole breaker might not always trip both poles simultaneously in a fault condition on a 240 volt circuit, especially if the fault current isn't high enough to trip both poles independently. This is why electrical codes typically require a true two-pole breaker for 240 volt circuits serving appliances like heaters. Two-pole breakers are designed and tested to ensure that both poles trip simultaneously under various fault conditions, providing a higher level of safety. They also often have a higher interrupting capacity, meaning they can safely handle larger fault currents without failing. Let's delve into the possible scenarios that can cause a breaker to trip, focusing on how these scenarios play out with a two-pole breaker versus a single-pole or tied single-pole breaker. Ground faults are among the most common reasons for a breaker to trip. A ground fault occurs when a hot wire comes into contact with a grounded surface, such as a metal enclosure or a ground wire. This creates a low resistance path for current to flow back to the source, resulting in a large surge of current. With a two-pole breaker, if a ground fault occurs on either of the 120 volts legs, the breaker will trip both poles simultaneously, cutting off power to the entire circuit. This protects against electrical shock and reduces the risk of fire. However, with a single pole breaker, only the affected leg is disconnected. The other leg remains energized, potentially posing a shock hazard if someone comes into contact with the grounded surface. Even with a tied single pole breaker, there's no guarantee that both poles will trip simultaneously, especially if the ground fault current isn't high enough to trip both poles independently. Another common cause of breaker trips is overcurrent. Overcurrent occurs when the circuit draws more current than it's designed to handle. This can happen if the heater is faulty and drawing excessive current, or if there's a short circuit between the hot and neutral wires. With a two-pole breaker, an overcurrent condition on either leg will cause both poles to trip, protecting the circuit from overheating and potentially causing a fire. The breaker is designed to trip at a specific current rating, such as 20 amps, and it will do so regardless of which leg the overcurrent occurs on. With a single pole breaker, only the affected leg is disconnected. The other leg continues to supply power, potentially leading to further damage or a fire if the overcurrent condition persists. A tied single pole breaker might trip both poles in an overcurrent situation, but it's not as reliable as a two-pole breaker, which is specifically designed to handle overcurrent conditions on 240-volt circuits. Loose or damaged wire connections can also cause breakers to trip. Loose connections create resistance, which generates heat. This heat can damage the insulation on the wires, leading to short circuits or ground faults. Damaged wires can also create similar problems. With a two-pole breaker, if a loose or damaged connection causes a fault on either leg, the breaker will trip both poles, preventing further damage. With a single pole breaker, the problem might go unnoticed until it escalates into a more serious issue. A tied single pole breaker might trip, but it's not as sensitive to these types of problems as a two-pole breaker. It's also important to consider the interrupting capacity of the breaker. The interrupting capacity is the maximum amount of fault current that the breaker can safely interrupt without failing. Two-pole breakers typically have a higher interrupting capacity than single-pole breakers, making them better suited for handling high fault current conditions. If the fault current exceeds the breaker's interrupting capacity, the breaker can fail, potentially leading to a fire or explosion. Now, let's focus on the essential wiring considerations for heater circuits. The first and foremost consideration is the wire gauge. The wire gauge must be appropriate for the amperage draw of the heaters. Using undersized wires can cause them to overheat, leading to insulation damage, short circuits, and fires. The National Electrical Code, also known as NECE, provides tables that specify the minimum wire gauge required for different amperage ratings. The specific table to consult will depend on the type of wire being used and the installation conditions. However, as a general guideline for 20 amp circuit, 12 American wire gauge, also known as AWG copper wire, is typically required. For a 30 amp circuit, 10 AWG copper wire is usually necessary. It's always best to consult the NEC and local electrical codes to ensure compliance. Remember that aluminum wire has a higher resistance than copper wire, so it requires a larger gauge for the same amperage rating. Aluminum wire is also more prone to oxidation, which can lead to loose connections and overheating. For these reasons, copper wire is generally preferred for heater circuits. The circuit must include a ground wire. The ground wire provides a low resistance path for fault current to flow back to the source, allowing the breaker to trip quickly and safely. The ground wire should be connected to the metal enclosure of the heater and to the grounding system of the electrical panel. This ensures that any fault current will be safely diverted to ground, minimizing the risk of electrical shock. The ground wire should be the same gauge as the circuit conductors. It's also important to ensure that all wire connections are tight and secure. Loose connections can create resistance, which generates heat and can lead to fires. Use appropriate connectors for making wire connections, such as wire nuts or crimp-on connectors. Make sure the connectors are properly sized for the wire gauge and that they are securely fastened. It's also a good idea to use antioxidant compound on aluminum wire connections to prevent oxidation. The heater should be properly installed and maintained to prevent any safety issues. Follow the manufacturer's instructions carefully when installing the heaters. Make sure the heaters are properly grounded and that they are located away from flammable materials. Regularly inspect the heaters for any signs of damage, such as frayed wires or cracked heating elements. If you notice any problems, disconnect the heater and have it repaired by a qualified electrician. Do not attempt to repair the heater yourself unless you are qualified to do so. It's also a good idea to have a qualified electrician inspect your electrical system periodically to ensure that it's in good working order. They can identify potential problems before they become serious safety hazards. This is especially important for older homes, which may have outdated wiring or electrical panels. If you are not comfortable working with electricity, it's always best to hire a qualified electrician to do the work for you. Electricity can be dangerous, and it's not worth taking risks. A qualified electrician has the knowledge, skills, and experience to safely and correctly install and maintain electrical systems. They can also ensure that your electrical system complies with all applicable codes and regulations. By following these guidelines, you can ensure that your heater circuits are safe and reliable. Remember, electrical safety is not something to take lightly. Always take the necessary precautions to protect yourself and your family from electrical hazards.